right?
Great. Right. Hi, everyone. I'm Nivedita Bijlani. I'm the TA for the data mining program, and we're going to talk about association rules in R today. This is module 2, um, and it's a pretty short week compared to module 1, where you had 2 weeks. So I'm going to try and keep it as short as possible because obviously you have a lot of readings, exercises, assignments to go through. As you can see from my screen, we're going to make sure that everyone is on mute, as Yelena has just said. And let's leave the questions for the end, or you can post them in the chat and we'll pick them up at the end. So the structure is going to be something like this. I'm just going to go through a few slides. You can see here I have just about 11 or 12 slides. And we're going to do a code walkthrough. You're probably going to be familiar with a lot of the code from the exercises because I think that kind of walks you step by step. But I'll still just go through another example. And the idea really is that I'd like to walk through an example which is different from the one that is in the exercise and the assignments, and give you the opportunity to ask questions while also distilling the information in fairly simple terms. A lot of the readings this week are highly technical. There's a lot of maths, equations, formulas, etc. So we're just going to distill it down and go through the code. So yeah, as you can see here, the agenda will be, we do a quick recap of concepts. Then we go through the steps to extract association rules given a data set. We walk through the method in R. And as I said previously, questions and answers at the end. Right. So now we are on association rules, the what and why. So association rules, as we see from the first point, these help identify probable relationships between variables in our data. So these are variables, these are outcomes, these are events that occur in our data set. Association rules are really important. They actually form a very important foundation for data mining. And one of these techniques is finding associations or analyzing patterns in data. So what we're doing here is we're trying to focus on finding out which events or which transactions tend to occur together or have a high probability of occurring together. And they occur together not just by chance, but they occur with some regularity. In fact, enough regularity that we could consider it a rule. This rule then becomes the basis for predicting future events or transactions. It forms the basis for data-driven decision-making in business or in any kind of enterprise. And as we see here, this idea has been used by enterprises for forward planning and for proactive decision-making. Association rules have a number of different applications across several different industries. And some of the ones that I've mentioned here are retail, in which the shopping basket analysis is perhaps the most common example. In medicine, where we can look at patients' symptoms and try and predict certain outcomes. In predictive policing, which is a very important application of association rules today, what are the characteristics of certain kinds of people, certain kinds of demographics, certain kinds of race, where people live and so on, and we can pick up patterns from data. Then, of course, you'll be familiar with recommender systems like, those are behind Facebook, Netflix, LinkedIn, etc., which kind of take simple association rules to the next level. And again, just to kind of summarize this slide, what we're trying to do here is we've got basic principles. If we apply basic principles of association rules, we can get very quick and powerful insights. Then we come to the basic parts of association rules. An association rule has essentially two parts. The technical term is antecedent. Ante stands for before. Antecedent, which is if this, and the consequent, which is the right-hand side, which is then this. So an antecedent is the item found in the data. On the left-hand side, consequent is found in combination with the antecedent on the right-hand side. So I've just given a couple of examples here. We've got, for example, you buy color pencils and paint brushes, and there's some probability that you will also then buy drawing paper. Another example, if you buy bread and butter, chances are you will buy eggs, cheese, and milk. So we've got this as the left-hand side, or the antecedent, and this as the right-hand side, which is the consequent. These items, so as I said, we've got the left-hand side item set, and then we've got the right-hand side item set. The combination of these two item sets on either side is called a rule. That means if the left-hand side is true, then there's a high probability that the right-hand side items go along with that. And if this combination occurs with a certain amount of regularity, which we define via a threshold or a predefined interest threshold, then we can call it a rule. Now, one important thing to remember with association rules is that while we're going to do a walkthrough and while a lot of the examples talk about fixed data sets, association rules are not usually set in stone. Data sets are constantly growing. There are new transactions, new events that are happening, and therefore these rules have to be updated accordingly. Another thing that we mentioned were these thresholds, and the two important terms here are support and confidence, which we will look at on the next slide. Just moving on to the next one. Right. So we've got the main terms related to association rules are support and confidence. A lot of people get confused between support and confidence. So we're going to try and again break it down into simple terms. So what we mean by support is that we look at the entire data set and we find the frequency with which an item set occurs. So as I've shown in the example here, if we have a support of 0.1 for this item set shown here, it means that cereal and milk leading to the buyer buying bread occurs in 10% of the observations in the data set. So support essentially means what is the support of this left-hand side and right-hand side item sets in the entire data set? How strongly does that data set support this rule or this set of transactions? The next term is confidence. In confidence, we only look at the left-hand side. So for example, going back to the cereal and milk example, how many times that when I buy cereal and milk, I also buy bread? So with confidence, we are not looking at the entire data set. We are looking at that portion of transactions in the data set where the left-hand side occurs. Once we count those transactions in which cereal and milk occur, we then find out in how many of those transactions bread occurs as well. So how confident are we that the right-hand side occurs when the left-hand side occurs? So again, the example that's given here is that a confidence of 0.7 for the occurrence cereal, milk, leading to oranges and apples means that in all observations that contain cereal and milk, 70% of those transactions will contain oranges and apples. So I hope the distinction between support and confidence is clear, because these are the cornerstone concepts of association rules. Right. Then another term that's associated with association rules is called lift. we don't look at support and confidence in isolation because uh, the rule consists of multiple items. We want to be sure that when they occur in combination, is that is that combined occurrence stronger than the probability of those items occurring individually? And that connection is given by the term lift. So I'll read out the definition here. Lift implies how strong is the combined occurrence of the left-hand side and right-hand side items in relation to their individual occurrence. So it's defined mathematically as the combined probability of them occurring together divided by the product of their individual, the probability of their individual occurrence. Now, if the lift is greater than 1, it means that the coming together of these item sets actually makes the rule stronger, or it occurs more frequently in the data set than each item set occurring individually. In contrast, a lift less than 1 implies that the combined occurrence of the left-hand side and right-hand side items is actually less frequent or weaker as compared to each item set occurring individually, and the combined occurrence undermines the strength of their individual occurrence. So again, in simple terms, this means that we are looking at support, we are looking at confidence, but we are also looking at the combined strength of, or the combined probability of the item sets occurring together compared with their individual probabilities of occurring together. Now, there are several other interest measures. We've got coverage, cosine, cross-support ratio, all confidence, conviction. Sorry, it's not casual support. It's casual support, casual confidence, leverage, odds ratio, and so on. I've included a link here, which I'm not going to click into because you should have this through the PowerPoint slides. But you can click into this link and it actually covers a number of these interest measures. And the idea is, depending on what the objective of your analysis is, you might be looking for connections between item sets which go beyond just support and confidence. It kind of, a knowledge and an understanding of some of these other interest measures will complete the picture of how these associations work more deeply. Now, in order to find these association rules, there are a couple of major algorithms. The one that we are going to focus on is the a priori algorithm. And again, I've kind of distilled down, all of the readings to these 3 basic principles of a priori that you just need to bear in mind. The first thing is, a priori is based on the principle that only smallest common subset of items that meet your support and confidence thresholds are retained. Others are discarded. So that's the first basic principle. Just to illustrate that with an example, if buying milk leads us to buying diapers, or if when we buy milk, we also buy diapers, we have an occurrence of 0.75, where your threshold is 0.7, then we keep this rule. As compared to another rule, where you have milk and bread on the left-hand side, diapers on the right-hand side, with a probability of 0.73, where the threshold is 0.7. Now, the reason why we're going to discard the second rule is because we already have a subset of its items that have a similar or a higher threshold. So that's the first principle of a priori. The second is the way in which a priori works. And it's important, I think, to understand at least to some level how these algorithms work, because when you're working in large-scale systems on large-scale data sets, you need to have some insight into how the algorithm works, where the pitfalls are, whether it's performance, whether it's how these calculations are done, etc. So I've just included a line there to say how a priori works. So what it first does is it goes through the data set completely. It scans the data set in full and counts the frequency for single items only. It generates a frequency table. It compares that frequency for each single item to the support threshold that we've defined for that data set. It could be 0.5, it could be 0.1, whatever, 10%, 50% of the transactions and so on. And it discards if it discards those items where the support is less than the threshold. Then it goes back to the beginning of the data set and it looks at combinations of items. So then it creates an item set of 2 items and then it generates a frequency table again. Once again, it applies the threshold and discards those transactions which fall below the threshold. Then it goes back. Sheila, shall we keep that for the end, or would you like me to pause where I am? Yelena, can we unmute Sheila?
Yes, or she can also type question in the chat. So, let me see. Sheila, yes, okay. Sheila, go ahead, speak, please. Sheila,
good morning.
Yes.
Hello.
Yes.
Hi. Thank you for stopping. Thank you for holding this morning. It's morning on Eastern Coast here. I wanted to know. So you said that you would discard the second milk and bread if then with diapers because the threshold for milk and diapers is higher. But if milk and bread is higher than milk alone, would you discard the other one too, or would you keep them both if they meet the threshold?
So yeah. So the idea is that what we are trying to do here is we are actually taking the smallest common subset of items. Now, milk and bread together cannot occur more frequently in the data set than milk occurs on its own. Can we see that? So milk and bread together is 0.73. It's supported 73%. It should be not 0.73%, but it's 73% of the time. And milk, therefore, will always occur 73% or more with greater frequency in the data set.
So if their frequencies were the same, would you keep them both, or you would still pick the one with the smaller?
We pick the one with the smaller. We pick the one with the smaller, and we discard the other one. We discard the other one, even though it meets the threshold.
Okay, thank you.
Yeah, because we are interested in the smallest subset. Shall I go ahead?
Yes, thank you.
Yeah. Okay, you're welcome. Right. So we've looked at how the a priori algorithm works. Now, one of the slight disadvantages of this algorithm is that it goes through several times. It goes through the data set several times, as you can see, for every set of items that it will create. So if it has to create a set of single items, it has to scan the entire data set. When it then goes back to find out the frequencies of 2 items, it again has to go back through the data set. And then it'll go back once again when it has to create a rule which has 3 items on the left-hand side and so on. Now, depending on the size of the data set, this will obviously go through multiple times, resulting in a high memory consumption. Now, for the data sets that we are looking at in this class, we have fairly small data sets, 1,000 records or even 10,000. You'll probably not notice any kind of performance bottlenecks. But if we are talking about tens or hundreds of millions of records, to go through that multiple times and actually apply the a priori algorithm in memory can be very expensive in terms of resources. So this was a priori, and this is the one, as I said, we're going to focus in the code walkthrough. Another one is called FP growth, frequency pattern. FP growth. Now, the way this works is it counts all the items in the data set, and again, it only retains those which are above your defined threshold, and it sorts these items by descending frequency. Then what it does is it uses all of the transactions it has retained from the previous step to build a tree of associations in memory. So essentially, what this is doing is it goes through all of the items, picks out the items which meet the frequency, and stores them in memory. Then it goes through the dataset one more time, and with each transaction that it encounters, it will add them to each, it will actually attach them to each of these items from the previous step, and it will make a tree of combinations in memory. At the end, it will then go through every branch and it will discard any items where frequency is less than the threshold. Now here, compared to a priori, we are doing two passes through the dataset. First, to form the individual items, and the second, where it goes transaction by transaction or record by record and adds to the tree in memory. So relative to a priori on a similar sized dataset, we might find that FP growth is actually more efficient. But as I said with the previous slide, for the size of datasets that we are looking at in this class, even if you were to do these comparisons, because the differences will be in kind of milliseconds, nanoseconds, we won't be able to notice any significant differences between the two. Right. Before we jump into the code walkthrough, I just wanted to outline the very general steps, whichever method you're using, whether it's a priori or FP growth or any other. Here are the basic steps that are used in order to extract rules. So the first thing that we do is that we set our objective. Now, with every data set, when you analyze a data set, there's got to be some objective with which we are examining the data sets. For example, are we interested in a particular outcome? Are we interested to see what conditions lead to a particular outcome? And what are these conditions that we are interested in? Then we explore the data. This is a really important step because we want to not only get a feel, get an intuition of how clean the data set is, we also want to have some idea of which outcomes are more frequent, which outcomes are less frequent. And it's important to do this before we actually jump into programmatically extracting information from the data set. We need to get an overview of where this data is collected and so on, because the rules that you then extract at the end of this process are going to reflect the data that you've seen. So for example, you might have a data set in which you have a particular column which has zeros and ones, or true and false. When you're exploring the data set, you say, well, a lot of these values seem to be true, and there's just hardly a few that are false. Now, that is going to be reflected in your rules, because if you then end up getting only true values in your rules, you have this at the back of your mind saying, yes, well, true is actually a more frequent value in the data. So no wonder or no surprise that there are no false outcomes in my rules. So it's just to get an intuition of your data set. Then the next step is to clean the data. So here what you want to do is to replace or eliminate missing values. You might want to replace codes with their descriptions so that, again, once the rules are extracted, they make sense to us. Then we do data preparation. And again, in the walkthrough that we look at, a really important part of doing this is binning of values. Because, for example, if you look at ages in age values in your population, you'll have people who are 62.5, you'll have people who are 60, 59.5, and so on. Now, what we want to do here is we want to abstract these outcomes. We want to make them a little bit more generic so that we can do pattern analysis. It's very difficult to do pattern analysis, or it's difficult to find patterns if we look at extremely precise and specific values. It's easier to notice trends if you group certain values together. Then the next step then is to choose the algorithm. And as I said previously, we're using the a priori algorithm. We decide the threshold values for support, confidence, the length of the item sets in the role. Now, these are really important because this again ties back to your objective. Are we looking for outcomes that occur very frequently? Because there's a critical decision that's kind of going to be based on that. If that is the case, you might decide that a support of 5% or 10% is not good enough. It needs to be 50% or 70%. Similarly with confidence, because if you're going to, for example, go and make decisions for your entire supply chain, you don't want to do it on the basis of transactions that occur maybe 20% of the time together. You might want a more significant presence of these factors in your data set. So these threshold values have to be decided and then fed into the rules engine. Then we do the extraction of rules using these threshold parameters, and this is the set of steps in R that we're going to walk through. Then a very important part is to remove redundant rules. We want to again distill down the set of rules that are returned back to us. And this is again done in a couple of different ways, which we look at. We might want to graph rules. Again, this is an optional step just to if the set of rules is very large, you might want a visual representation of it, so it makes sense, or you can pick up the few that you are interested in and that you might want to drill into further. And of course, the final thing is, again, it ties back to the objective. Based on what we've found, we recommend a course of action, we make decisions, or we come to some sort of conclusion. So as I said previously, whichever algorithm we are using, these are the basic set of steps that we want to follow. Right, so what we'll now do is we'll jump right into the walkthrough. The data set that I'll be using in the demo is a subset of what's called the CPS, or the Current Population Survey from 2013. It contains demographic and employment information from a wide range of Americans. There are 7,291 entries and 13 columns. And this data set is essentially a set of statistics that are used to gauge the strength of the American economy. These stats are collected every month, and this is the September 2013 version. The original data set, and I've just provided a link here if anyone's interested. The original data set has 385 columns and several millions of records. But just for the purpose of demo, we've got it down to about 7,000 entries and 13 columns. So I'm going to jump into the R code for this. What I've done is I've actually written it out beforehand, but I'm going to run through it line by line, just to kind of save on typing in this session. And at the end, we'll just open the floor to any questions. Right, so the first thing that I'm doing here on line 2 is that I set my working directory. Now, this directory is important because this is where my data set is. And rather than putting the full path names, if I set the working directory at the start, then I don't have to worry about changing locations and so on. So I do a ControlEnter to run the line. Once the line is successfully run, you can see in this console below that R has executed this command and it's ready to move on. The cursor is automatically placed on line 3. I'm reading the cps.csv file into a variable called CPS for current population survey. So I do control enter. Yep. And we can see, I'm just going to close that. And we can see here in this environment window that CPS is described by all of these different columns. Now, the environment window is really useful, as you've probably seen for your Module 1 exercises as well, that as you go through each and every command, as you execute each and every command, the variable values are updated, and you can always see the latest value in this environment window. So I'm just going to collapse that for now. Right. Let's explore the data. So that's the view command. What this does is it opens up the data set in a different window. And here it's formatted nicely as a table. And you can see the columns that I have here. We have the region, state, metro area code, age, marriage, gender, education, race, and so on. Just going to very quickly scroll across so you know what columns are being are displayed. Citizenship, employment status, industry. It's a fairly simple data set, and you might notice it's fairly clean as well. Right. Let's run the summary command. Now we can again see in the console window that it has taken each and every column in the data set and given you the important stats. The region is a categorical variable. 1,183 records have the region Midwest, 1773 have the region Northeast, and so on. Similarly, state. Now, metro area code, because it's a number, and we haven't done any processing on the metro area code, we haven't told R that we don't want to treat it as a numerical value. It actually gives you all the stats, the minimum value, the first quartile value, median, mean, third quartile, and max, as it would do for any numeric field. Likewise, for age, then again, married is also all of these columns, marriage, sex, education, race, etc. These are again treated as categorical variables, and then we've got some more numerical variables that R understands to be numeric down below. With your data set, I'd recommend that you actually spend a little bit of time trying to understand, what are the most frequently occurring values for categorical values, what the ranges are for numerical values, and so on. It just gives you a good, intuition, a good sense within your data set. For example, we've got 15 to 85 people aged 15 to 85 in our data set. Right. Then we run the str command, and what this is telling us is the data types for each and every column. And where we have categorical variables, it talks about how many levels, or what are the different levels are actually categories, how many levels there are for that particular column. Right. Now I can just run a few kind of exploratory queries. I don't have to, but just out of interest as I'm exploring this data set. So what I want to find here is, which is the most common industry of employment within this data set? And it says educational and health services. Which is the state with the fewest interviewees? Let's run that. That's Georgia, 7. What's the state with the most interviewees? That's Pennsylvania. Let's check for any missing values. Now, this data set doesn't actually have any missing values, but not every data set that we'll be analyzing will be as clean as this one. So we just want to make sure that we don't have any NAs. And we can see here that we get false for all of the columns. If you run it on a data set that you've just obtained as a raw data set from another website, you might have some of these set to true, and then you'll have to perform steps in order to remove these missing values, or replace them with sensible values, or actually take those entire records out of the data set if they're going to, to mess up your analysis. Right, now we jump in straight to rules. I've previously installed the A rules package, the A priori rules package in R. I've also already installed the A rules viz package, which is R's package for rule visualization. So those installation commands were run outside of this R program. And what I'm doing with the library commands here is to load them into memory so that I can now use them. And the reason I have to do this is because R doesn't actually load these packages by default into memory. It does, others, uh, which will, for example, allow you to use these table functions, the apply, tapply, sapply, and so on, but not the a priori rules. So I need to make sure that I load them, and they need to be loaded in this order as well, because the a rules viz package actually depends on the a rules package. So I need to do them in this order. So it does that, then I move on, and then it gives me some messages. Now what I'm going to do is to pre-process my data. We spoke in the steps to extract rules that we want to look at discretizing values or binning values, which essentially is again abstracting these values into a form that will be useful for pattern analysis. So in this case, I'm actually factoring up the age field in the data set. And what I'm doing here is I'm actually specifying the values for age bins or age brackets. And I'm then specifying the corresponding labels. So that's teen, young, adult, middle, and senior. So let's run that. Right. Let's also now do that for the field called Hispanic, because this was set in our data set as a set of zeros and ones. And as I said previously, R treats them as numeric variables. But what we want to tell R is actually it's two categories, 0 or 1, true or false. So let's explicitly turn it into a factor variable from a numeric variable. Done that. Now, for the purpose of my analysis, I'm not really interested in the metro area code or the country of birth code. And the reason is that the metro areas and the country of birth values in the data set are very varied. So we have, in this data set, we have people from more than 20 or 30 countries, and likewise with metro area codes. And I decide that instead of turning the country of birth code again into factors, that will again generate a huge number of rules, or actually it might not find me any records that comply with a particular threshold. So in order to simplify my analysis, I'm only going to be looking at age, Hispanic, and a few other fields. Now, in order to remove these columns, I'm going to turn them into null. So I do that for the metro area code and country of birth as well. Right, now we go deep into the rules. We start to extract the rules. The first thing we've done here is to simply run the a priori algorithm on the modified data set with the metro area code, the country of birth code removed. Let's do that. And let's look in the console window, and we find that we have, it uses by default a confidence threshold of 0.8 or 80%, and it will use a support of 0.1, which is 10%, which means that 10% is the minimum value or the minimum number of times a left-hand side item set has to occur in order for it to qualify. Now, if there are 7,291 records in the data set, the absolute minimum support count or the occurrence count will be 729, which is 10%. The minimum length of the item set is again by default set to 1. The maximum length is set to 10. Again, What this has done is if you go right to the end, it's generated 1,171 rules. Let's inspect the first 10. So we see that we've got the left-hand side, the right-hand side, each with the support, confidence, and lift value. Let's run the summary command. Right, so this gives me what's the minimum support, the maximum support, minimum lift, maximum lift, and so on. What I then want to do is, I want to actually isolate or filter out those rules where there is nothing on the left-hand side. Because essentially what this is telling me is that race equals white, citizenship equals this value, Hispanic equals this value, and employment status equals employed. These are actually rules that the data set is throwing at me. But when I'm looking for associations, I'm interested in some left-hand side having a consequence on some right-hand side. I'm not interested in properties or traits that occur in isolation. So what I would do is, because here the length of the item set is 1, I'm going to run the a priori algorithm once again, giving a minimum length of 2 so that these 4 rules then drop out. Let's do that. And you can see here that 1167 rules are left. So it's actually dropped out those other 4 which don't really mean anything in terms of association. In the next line, what we're going to do is to try and vary the support and confidence threshold. So I'm actually increasing the support and increasing the confidence threshold whilst keeping the minimum length as 2. I run that and I get 16 rules. So you can see that it's come down because the confidence values have gone up and the support values have gone up. Now I'm going to try and sort them by lift because I want really the ones that are the most important rules. I want them, I don't want rules which were, as I said, when we were discussing lift, I don't want to pick up those rules which have a low value of lift or have a lift value of less than 1. I want to sort them by lift. So let's do that. And you can see here that we've got the support, the confidence, and I've actually sorted these by lift. So if the maximum value of lift starts somewhere at 1.08, and then as we scroll down, the lift value decreases. I could also sort it the other way around by saying I want to sort by lift, but this time in ascending order, or decreasing is equal to false. And it's done it the other way around. In this code now, I've again provided a link where it talks about in greater detail than we've explored in this R code as to how we can, from our set of rules, how we can extract certain rules of interest. For example, if I'm interested in region equal to Northeast or region which is Northeast or Midwest, how I can search for these, how I can do partial matching, that's PIN, partial in, and I say region is North, it will bring up North as well as Northeast. If I want to do complete matching, then it's AIN or absolute matching or absolute in. I can provide certain other conditions, complete matching with an AND condition. So I say, well, region should be Northeast and the lift should be greater than 1.3. So there's a number of different ways in which we can pick out those rules that we are interested in. So I'm going to just skip through here, but of course, as Yelena said previously, the PowerPoint slides as well as the code will be available for you to download. So feel free to run these in your own time. Right. Now what we're going to do here is, again, one thing we are doing here is taking a subset of the rules where the support is greater than 50%. So let's run that, and we can get a summary. And we can see here in the summary that where the item set length is 2, we have 1 rule. Where the item set length is 3, we have 1 rule. item set length is 4, we have one rule. Right. I'm just going to, this is another way of subsetting the rules. So I can show the rules that have region equal to northeast on the right-hand side. And this is how it's done. I think there's an example of this in the exercise as well. Let's do that. We've come up with 6 rules where the right-hand side has region equal to northeast. Let's have a look at that. Right, so that's your right-hand side. We can also have 2 conditions for the right-hand side. The employment status is employed, and citizenship has the value citizen, native. Minimum length is 2. So this is just an illustration of the flexibility you have when you're running the a priori rule on a data set. Right? So here we come up with 335 rules. Now note here that we have not, in line 91 here, we have not provided values for support and confidence. So it actually picks up the reason why you have a large number of rules here is that the support and confidence values are the ones that are set by default and not provided by us. Right. Then we come to pruning of rules, and this is perhaps the most important part of the exercise because, as I said earlier on, if we simply run the rules engine by default, it automatically throws up a large number of rules. And sometimes the number of rules can be too large to analyze. And what we want to do is to try and prune the set of rules that make sense or we can actually individually look at for analysis. So the first thing I'm going to do here is I'm going to sort the rule set by lift. And notice here that it is in descending order by default. So we run that. Now, let's pay a little close attention to finding redundant rules. Now the first method of finding redundant rules is the one that's provided in your exercise, and it's absolutely fine if you use this because it works, and it's the way redundant rules have been kind of found. Then I'll also go through a more efficient method of removing redundant rules, which is with this command called isRedundant, which actually takes away the need to write these extra 4 or 5 lines of code. You're absolutely free to use whichever method you wish. So let's go through the first method. Some of you may be wondering how this method actually works if you've seen this in your exercise. Again, run through it very, very quickly. So what we're going to do is we're going to use the rules.sorted variable, or the set of rules that have been sorted by descending order of lift. The first thing that we do here is we create a matrix which tells us which set of rules is a subset of which other set of rules. And I've got a little Excel file here that I just wanted to, I'm going to run this, of course, but in order to visualize it easily, I'm just showing you in Excel what this looks like. So what this is doing is it enumerates every rule on as a single row, down this side. And again, it takes, every single rule and it puts it across the columns. So what it is doing is it's finding for every rule against every other rule, it tries to match them up and say, is this a subset of this rule or not? The way we read this is to say, is this rule a subset of this rule, which is actually the same rule? This is number 1, this is number 1. So the idea is, yes, it is a subset. Then it takes the second rule and it says, is this a subset of that? We say 0. Is the third rule a subset of the first one? And then we put zeros and ones, and this is how we populate the entire matrix. And you will find that every rule, and if you look down this diagonal, it's actually, they will all be ones because when we look at one rule and compare it to itself, it's essentially a subset or a duplicate of it. So this is how this is the reason why we use the subset matrix. One of the disadvantages here is that if you have a large number of rules and you make this kind of matrix, what you're essentially doing is, if the number of rules is n, you'll get a matrix which is n square in size. And that can be massive. And that is the reason where the second method is actually far more efficient. But let's just quickly go through this. The next step that we're going to do is to set the lower triangle. The lower triangle is essentially, I won't be able to select it like this, but where we see these ones, you can see that this kind of line comes down a little bit like that. We set the lower triangles to be false or 0. And the reason for that is that the way this particular algorithm works is that we've got repeated rules on the upper triangle because it doesn't consider the left-hand side and right-hand side matching to be kind of side-specific. For example, this particular algorithm, the way it works with subset.matrix, it means that if, for example, rule 2 is a subset of rule 1, then rule 1 is a subset of rule 2. So there are a number of duplicates in this matrix. And what we want to do by setting the lower triangle to 0 is that we want to remove those duplicates. So what this is saying is set the lower triangle, including the diagonal elements. And we've seen that the diagonal elements are those values where each rule is compared against itself, because that's where the rows and the columns intersect with each other. So we set them to false. Once we do that, then we are simply in that line summing up all of the ones. We are taking column sums, and we are only interested in those where the column sums are greater than 1, greater than or equal to 1. Because where the column sums are 0, it means that no rule in that row is the subset of any other rule. So we pick up the redundant rules. Now, I'm just going to run it. Let's see where so I've already run that line. Let's set the lower triangle to false. Let's do that. Control-Enter. Now, redundant will give me true or false. So the size of redundant is exactly the same as the size of the original rule set. However, it will only have true and false set where there is redundancy or there isn't. So what I'm interested here is not the complete redundant matrix, but the matrix where the value of redundant is true. So let's run that and let's find out the length. And that is 6. So there are 6 redundant rules. Let's display them. So we've got them here. And the head is again works in exactly the same way. It's just doing the exact same thing as line 107. So that was the matrix way of finding redundant rules. We essentially make a matrix, we set the zeros and ones, we set the lower triangle values to 0, and then we calculate the sum across every column, and we are only interested in those where the column sums, which are greater than or equal to 1, those are the redundant ones, and we pull out the rest. All of this is now done more efficiently, and as I said, you're very welcome to use either method. This is more efficient, and all this is doing is it's using this function which says is redundant. It's running on this sorted set of rules based on confidence. So let's do that. Let's run that, and I look at the pruned set of rules. So you can see there are 10 rules here and 6 were redundant. So that's 10. Let's look at the summary. It again gives me that. Let's do the length. That already. Right. So that's how we remove redundant rules. So now we've got a manageable set of rules that we'd like to visualize. It's 10 rules. The last part of this walkthrough is looking at visualizing rules. Again, you can absolutely work with the textual description of rules, but sometimes it's really easy to look at a scatter plot or a graph plot and make sense of, you can easily pick out which rules have greater support, confidence, lift, etc. So let's just draw a default scatter plot. You can see we've got a scatter plot for 10 rules in this window. And if I click zoom, it just zooms it into a larger and a separate window. And you can see these different points. The nice thing here is that actually you've got 3 dimensions of the data. So you've got the support, which is plotted with the confidence, and the color is the 3rd dimension. And here is a little key that says as the lift goes up, the rule is highlighted in a darker shade of red. So we close that. That's one way of visualizing it. And you can see, for instance, this particular rule has a very high support and a very high level of confidence, as well as a high value of lift. So 1, 2, these rules you might be interested in just to explore a bit further. Let's look at a graph. Right, so we've got this. Let's try and zoom here and see. Right. So this is again quite an interesting way of visualizing, because here again you've got kind of 3, you've got 3 elements of information here. You've got support, you've got colored by lift, and you've also got the associations, what leads to what, or what has a consequence of what. Right, let's move on. Let's try this. Right, so we've got this support confidence, and here you can actually specify the parameter that you'd like for shading. So earlier we had shaded it by lift or support. Now we're doing it by confidence, and then we can shade it by lift again. There we are. Let's go to the next graph, which is a grouped graph. Let's try and zoom on that. Right. So this is again quite an interesting one. You can see the rules which have a high value for support. You have items in the left-hand side group and items in the right-hand side group. So it's almost like a two row matrix where the outcomes are two different outcomes are provided, and the corresponding rules that lead to that right-hand side are plotted. Right, let's move on. Then we have a 2-key plot. And again, you can explore these from the link that I provided. Let's again zoom. The order here is the number of items in the item set. So we've got again confidence, support, and the colors that are provided here. Now, one thing to say is that if you switch on the interactive mode, some of them, you can set a parameter when you're graphing these rules to say interactive is equal to true. And when you do that, you can actually take your mouse and click on these different points. And as you click, it actually brings up the description of that rule. So that can be quite handy. Let's do the paraquad graph. That's there. And that again kind of talks about how these different items and their values are associated with each other. Then we have the matrix plot. So you've got these there, the left-hand side, the right-hand side, ordered by lift. And then you can also have a 3D matrix. And I encourage you to look at the documentation because there are so many parameters that you can pass into the plotting method. You can make them look pretty, you can provide titles, you can provide legends. um, and you can pick out the rules that are interesting for your particular data set. Right, I think that now kind of brings us to the end of the walkthrough. I'm going to go back into the presentation. That was the last slide, essentially, and very happy to take questions if you have any. I'll, of course, be checking into the classroom as well to answer any questions. But if there's anything specific in terms of the slides or the R code, then feel free to bring it up.
Oh, someone is asking to show the interactive again, the animation, I think.
Animation? Which particular one?
Well, it says please show interactive modes during plot again. The interactive one.
Mm-hmm. Let's try this one then. Let's try that one. Right. So you can see that my mouse has now turned into a cursor. So if I click, let's just bring up the console window. If I click on that, or it says that one. Let me try and hang on just a second. We've got inspect, filter, zoom in, zoom out, and then let's try that one. Sorry. Why it doesn't actually come up with particular. Select a region with 2 clicks, right? And we click inspect. So when I clicked inspect, you can see that it's actually brought up a bit more detail here. So it's brought up the rule, it's provided the list, and it's provided the order. Order is essentially just the length of the rule set. So that's how the interactive mode works. And in order to stop the interactive mode, you just have to go and click outside the graph. Or you can just click stop from over here. Is that okay? Yep. Any other questions? Great, Sheila. Any other questions from anyone? Like I said, the R code, the PowerPoint will be available to you. So you can set it up within your own environment and go through it. Or you can ask questions in the classroom again. Right, is that it, Yelena?
Somebody is asking about the assignment. Okay.
Right.
Basically, for the assignment 1, there is a set of data sets posted in a classroom. And those data sets were selected because they're suitable for this assignment. And also they were tested that they load in R. So that's one reason. If you choose another data set not posted in a classroom, make sure that it has at least 300 data rows, and also make sure that it's suitable for the association rules exercise, and that it loads in R. Because some of these data sets are actually, I'm the one who posted the choices, and for some of the data sets in there, I had to do a little bit of tweaking for them to load into R. All right. Did it answer the questions? For exercise, yes, you have to use a data set that's given. For the assignment, well, it's going to be your call, but if I were you, I would pick from the choices provided. Yeah. Looks like I answered it.
Okay. Any other questions? Okay, I'm not seeing anything. Do you have anything else, Yelena?
Oh, I see somebody asked, and
Uh-huh.
for we only use a priori association rule. I'm not quite sure what the question is. I'm so sorry, I'm not quite sure because it says, the question says, and for we only use a priori association rules. I'm not quite sure. So I may have to, oh, for that assignment is association rules, right? But later in the course, there are going to be assignments for other data mining methods. But for this assignment, we just focus on a priori association rules, that's right. Well, yeah. Sure, you're the most welcome, yeah. Well, because some questions were directed to everybody, some questions were directed to you, and some questions were directed to me, so that's why.
Okay, right.
Mm-hmm.
I'm not seeing anything else. Does anyone else have any questions? Is that it? Anything else coming your way, Yelena?
Not yet, but
Okay.
the way, well, if you guys don't have a question, then the presenter will start asking questions. Pop quiz.
Is the quiz is graded?
Well,
Quiz is
maybe,
graded.
but the grade does not count towards the course average.
We'll get a free ice cream.
Once the class is over, maybe.
Okay, well, yeah, thanks everyone. I mean, nothing else from me. I'm happy.
Thank you, Nivedita. Thank you, Elena. It was a great class.
Thank you. Yeah, and we'll try to have more classes like this if it helps, right?
It definitely helped us. For me, it definitely helped, and it clearly cleared some of my questions before doing this assignment.
Excellent. So we're gonna try to have another class on other topics. All right?
That would be great.
Sure. It's a customer service. Oh, okay.
Okay, Elena, thank you so much for being here and for recording.
Sure. And I'm gonna end the recording. And as soon as I receive the link, I'm gonna convert it to YouTube, and I'm gonna post all the files in the classroom in all sessions. We have two sessions this summer. Okay.
Perfect. Thank you so much. Thanks, everyone. Thanks for joining.
And yes, thank you.
Bye-bye.
Thank you. Bye.
Bye.